right? So let's look at question 1.3. A car of mass m traveling at speed v stops in time t when a maximum braking force is applied. If the same braking force is now applied to stop a car of mass 2m traveling at speed v, time taken to achieve this will be. So the information that we're given here is mass of an object, and we're given the speed, time, and we are told that the force is applied. So we will invoke the impulse momentum theorem here to respond to this question. So let me write down the equation. Theorem equation is impulse is change in momentum, right? And we are asked for time, so I will solve for time here. So t is change in momentum over force divided by force, and since the information contains the mass and speed, we'll expand this as m v final minus v initial divided by f there, right? So then if this time t is for the object mass m, and now we want time that it will take to stop an object, a car of mass 2m. So let me highlight this again, this stop here, use a highlighter here, and stop there. This indicates that our final velocity is 0. So stop means that the final velocity is equal to 0. So then we deduce that, and since they have the same initial speed, so we deduce that the change in velocity for both cars is the same. So v final for car with mass m and v final for car with mass 2m is 0, and both of them, they start with the same initial velocity v, and the same force is applied. So then we want the relationship between the time and mass, and we can see from this equation that time is directly proportional to mass. So then this means that if mass changes from m to 2m, then we have time is going to also double. So t is going to change to 2t. So therefore, the correct answer here is D. Time is going to be twice as much. Look at another question, 1.3. We have two trolleys, trolley A and B, with masses half m and 2m respectively, connected by the spring as shown in the diagram below. Trolleys are initially at rest. Ignore all types of friction. When the spring is released, both trolleys have a momentum with a magnitude of p. Trolley B moves with a velocity v to the right. The magnitude of the velocity of trolley A will be, so we must first write the equation for momentum. Equation for momentum is P is equal to mv, and we want to determine the velocity of trolley A in terms of the velocity of trolley B. So then this equation, we will write it as v is equal to momentum divided by mass, and we read it as velocity is inversely proportional to mass. So let's look at the relationship between the mass of trolley B and the mass of trolley A. We see that the mass of trolley B is 2m. So if we, how do we change this 2m to half m? So if you change 2m to half m, then that's division by 4. So you've changed the mass by a quarter. So 2m to 2m So since the velocity is inversely proportional to mass, then the velocity of trolley A is going to be 4 times the velocity of trolley B. So then the answer here is D, right? So let's look at another 1.3 that we have is ball moving horizontally as a constant momentum P and kinetic energy K. The ball collides with the wall and bounces back horizontally. Immediately after collision, the ball has a momentum half P. The mass of the ball remains constant. Which one of the following is the kinetic energy of the ball immediately after the collision with the wall? We will write this, we will respond to this question. Must recall from the proportionality videos, express that K, kinetic energy, in terms of momentum, is E squared divided by 2 times mass. So then, this is the initial kinetic energy of the ball. So now, this relationship states that the kinetic energy is directly proportional to the square of momentum. So if momentum changes by half, then the kinetic energy will change also by half, but squared. So that's going to be half squared, which gives us 1 over 4. So the new K, K prime, is quarter of the original kinetic energy. So correct answer here is A. Okay. Look at 1.4. A ball is dropped from a height h and strikes the floor with momentum p. The ball is then dropped from height 1 over 2h. Ignore the effects of air friction. Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from the height 1 over 2h? Right? So again, here we will look for the equation that relates height and velocity. So this is another projectile motion. So we know that the momentum is related to velocity by equation. Momentum is mass times velocity, and the equation that relates displacement and velocity. So we have to take note that, let me highlight the dropped part. Highlight that if it's dropped, then the initial velocity is 0. So we have the equation is v final squared is v initial squared plus 2 times acceleration delta y. Then the initial velocity is 0, so we'll have v squared is equal to, so this is our final velocity. I will name it v, is equal to v squared is equal to 2 g h. And then this implies that the velocity is the square root of 2gh. And then what happens is that if you change h by a factor of 1 over 2, then our v prime is going to be the square root of 2g h over 2, which is equal to the square root of 2gh over square root of 2, which is 1 over root 2 times the original velocity, which is square root of 2gh. So the correct answer there is number B, 1 over root 2 p times p. Since so I'm deducing that since the momentum is directly proportional to velocity, so if I change the velocity by the new velocity is 1 over root 2v. So then the momentum is also going to be 1 over the square root of 2 times the original momentum. And then let's look at 1.4. An object of mass m is accelerated from velocity v to a velocity 2v, as shown in the diagram below. So what is the net work done on an object? So we will invoke the work energy theorem here. Work net is change in kinetic energy. It's change in kinetic energy, which is final kinetic energy minus initial kinetic energy. And the kinetic energy is half m v squared there, right? So when we want net work done, we basically want to determine the change in kinetic energy. So since the kinetic energy is directly proportional to the square of velocity, so if this is our initial kinetic energy, then our final kinetic energy is going to be, if I double v, then my final kinetic energy is going to be the square of the initial kinetic energy, which is equal to 4 times the initial kinetic energy there. So then the change in kinetic energy is going to be final kinetic energy, okay, final minus initial kinetic energy, which is 4 times k initial minus k initial, which is 3k initial. And so then therefore the work net is equal to 3k initial, which is 3k initial is just half m v squared, which is 3 over 2 mass times square of velocity. So the correct option there is C. Right, question 1.4. Two masses MA and MB placed at a distance r apart. The third mass MC experiences a zero resultant horizontal gravitational force when it is placed 3/4 r from MA on the line between MA and MB. You must determine the ratio of the two masses MA is to MB. You must first note that if MA is r, this is r, the distance between MA and MB is r, and the distance between MA and MC is 3/4 r, then the distance between B and C is equal to quarter r. If the masses were the same, if MA had the same mass as MB, then since MA is 3/4 from MC and MB is a quarter from MC, then the force that A exerts on C would be 9 times smaller than the force that B exerts on C if the masses were the same. So the fact that the MC experiences a zero resultant force, conclude that the masses are definitely not the same. And from Newton's law of gravitation, Gm1 m2 over r squared, the force is inversely proportional to the square of the distance. So then, in order for the magnitude of that A exerts on C to be equal to the magnitude, the force that B exerts on C, then it means that the fact that the distance would reduce this force by 9, and in order for these forces to be the same, must conclude that the mass must counteract that. So the mass must be 9 times bigger than mass of MB. So then mass MA to MB is 9:1. So correct answer there is D. Of course, you can calculate, you can use a calculation for this as well by saying that F at A and C is equal to F, B, and C. And then you can have your G, mass A, mass C over RAC is equal to G, M, E, MC over RBC, R squared there. And then that will give you G, MA, MC divided by, from A to C, we have 3/4 squared will be G, MB, MC divided by quarter R squared. Then we can cancel out these ones there and the R squared as well, which would give us the R squared over 4, and then that will give us MA over 9 is equal to MB over 1. So then we conclude that MA to MB is 9:1.